On a quiet November morning, one tiny number changed. No alarms sounded, no sirens, no flashing red buttons, just a subtle shift in a live telemetry feed. A tenth of a degree, barely more than a rounding error. Yet that flicker nudged an interstellar object toward Earth's orbit. Inside a European tracking center, one analyst realized what it meant. Comets do not make clean, surgical turns toward moving planets. Craft do. As we unpack why something from deep space may be targeting Earth, help this investigation reach more people by hitting like and subscribing before we dive in. The story begins at the European Space Agency, in a room filled with screens and softly humming servers watching the sky in numbers. At around 10:51 Universal Time on the 22nd of November, a single line in a tracking terminal shifted. The object was 3I Atlas, an interstellar visitor on a hyperbolic, one-way path past the Sunday. Its course had been modeled, checked, and filed away as another rare, but ultimately harmless, cosmic tourist, until that one number moved. To almost everyone, the change would have looked trivial, less than a tenth of a degree in inbound trajectory. The kind of deviation that is usually blamed on sensor drift, thermal noise, or a fresh calibration pass. But to Felix Morvan, a young analyst working remotely from Darmstadt in Germany, that shift was not noise, it was intent. Felix watched the update propagate across the tracking display. 3I Atlas was supposed to hold to its outbound curve, sliding past the sun and out of the solar system forever. Instead, the new vector tilted very slightly toward the plane of Earth's orbit. Not a wild swing, not a chaotic tumble, a neat, exact adjustment. Enough to matter, small enough to hide in the rounding. Natural comets do move under their own exhaust. As ice turns directly into gas, jets erupt from their surfaces. Those jets produce tiny thrusts that can nudge a comet off its predicted line. The key word is tiny. The key pattern is messy. Outgassing flickers on and off, changing with rotation, fractures, and sunlight. It makes motion noisy and irregular, not surgical and clean. What Felix had just watched was the opposite of messy. The telemetry described a single angular change, a step rather than a stumble. 3I Atlas did not wander into a new path. It selected one. That was enough for Felix to push the data upward. His supervisor reran the numbers, checked them against independent solvers, and then quietly escalated the case into a closed thread inside the European Space Operations Center. Within 45 minutes, the object changed label. In a metadata field that almost no one outside mission planning ever reads, its status flipped from interstellar transient to capture candidate. Pending orbital confirmation. No press release, no tweet, no emergency banner. Just a new word tucked deep inside a database that only a handful of people can see. Capture is not a casual term in orbital mechanics. For an object that came in on a hyperbolic path, capture means a fundamental change in fate. It means something that should have been flung back into interstellar darkness is now flirting with staying. To be captured, a body has to lose energy, to slow down, or to be redirected by forces strong enough to bend its future into a loop instead of a line. In a textbook, that can happen through gravity. A planet or a moon can steal momentum and pull a passerby into orbit. In practice, for an object like 3I Atlas, it should be almost impossible near Earth. Our planet is small on the cosmic stage. Its gravity is not strong enough at these distances to grab an interstellar stone on a fast outbound arc. At least, not without a lot of help. There is another subtle force at work in the inner solar system. Solar radiation pressure, the push of sunlight itself. Photons slamming into dust and metal can shove trajectories over time. That pressure can bend tails, spread debris, and bias the paths of ultralight objects. It is slow, diffuse, and relentless. What it does not do is produce a single sharp kink in a trajectory in the span of one tracking update. The change seen at 1051 was not the fingerprint of gentle photon pressure. It looked like a burn. As updated coordinates flowed out to partner centers, the models were recalculated. The Jet Propulsion Laboratory in the United States fed the new numbers into its orbital solvers. The conclusion matched the European result. If the new vector held, 3I Atlas would cross the plane of Earth's orbit in roughly 38 days. Not on a bullseye collision path, but on a narrow intersection arc. Imagine threading a moving needle from millions of kilometers away. The Earth is not a static target. It races around the Sun at nearly 30 kilometers per second. To drift casually into its orbital plane near the exact time our planet will be passing through is unlikely. To do it, after a clean, sudden course change, is something else entirely. Inside control rooms, the language began to shift. This was still officially a comet. Public trackers still showed a graceful curve that never came close enough to worry anyone. Yet the internal notes now described alignment, synchronization, and capture windows. The kind of phrases engineers use for spacecraft, trying to rendezvous with a planet or a station. No one could point to a visible force. There was no erupting jet on the sunward side, no explosive outburst, no flaring tail. Telescopes saw motion without seeing cause. On paper, that should not happen. Without force, there is no change in momentum. Without a push, there is no turn. But 3I Atlas turned anyway, and its new path threaded closer to ours. Felix had started that morning as one name on a long list of analysts watching routine feeds. By noon, his quiet flag on a tenth of a degree had triggered a cascade of reclassifications, restricted folders, and late-night phone calls between agencies. An object that had been background noise was now a capture candidate with a future that intersected our own. From this moment forward, the question hanging over every model was simple and deeply unsettling. Are we watching a strange comet reacting to hidden physics, or are we watching a vehicle adjust its course toward a very specific moving world? 3. Atlas was no longer just passing through. In the numbers, at least, it had started to act like it wanted to stay. To understand why that tiny vector change was so unsettling, we need to remember how comets are supposed to behave. Because if you and I went looking for the most chaotic, unpredictable objects in the inner solar system, we would probably start with them. Comets are not quiet, disciplined travelers. They are cosmic spray bottles. They leak, vent, flare, and shed. That mess is exactly what makes them beautiful in telescopes and predictable on paper. A classic. Comet is a frozen mix of rock, dust, and volatile ices. As it falls toward the sun, sunlight starts to bite into that surface. Ice does not melt the way it does on Earth. It skips the liquid phase and turns straight into gas. That process is called sublimation. Gas bursts out through cracks, carrying dust and ice grains with it, wrapping the nucleus in a fuzzy atmosphere we call a coma. Then solar radiation and the solar wind get to work. Photons and charged particles stream outward from the sun and push on that loose material. The dust tail bends away like smoke in a breeze. Ionized gas forms a straighter, ghostly blue tail that also points away from the sunday. No matter where the comet is on its orbit, the direction is always the same. Tails point out, never in. This entire process is messy by nature. Sublimation happens wherever sunlight finds a weak spot. Vents flicker on and off. As the comet spins, jets fire in different directions. The result is uneven thrust that can nudge the orbit, but always in a sloppy, jittery way. You can think of a natural comet as a lumpy spinning rock with dozens of tiny fire hoses on it, spraying at random. Now hold that picture in your mind and compare it to what was happening with 3I Atlas on that November morning. Telescopes across the world were watching it. Infrared instruments were checking its temperature. Spectrometers were sniffing for gas. If this was a normal comet approaching the inner solar system, the sun-facing side should have been heating up fast. At that distance, water ice, carbon dioxide, and other volatiles should already be boiling away. The coma should be expanding. The tails should be forming. Observatories should be picking up the fingerprints of water vapor, carbon monoxide, carbon dioxide, and dust. Instead, they saw almost nothing. Infrared readings from a space telescope showed that the sun-facing side of 3I Atlas was cool. Not just cool, compared to the surface of the Sunday cool. Compared to what physics says is needed to start serious sublimation. A temperature profile that low means the ice should still be locked in place. No boiling, no venting, no thrust. Yet the orbit had changed. The vector had shifted in a single clean step. The path bent closer to the plane of Earth's orbit. Motion without a visible cause. That is the paradox that started to haunt the analysts. Ground-based telescopes checked again. No asymmetry in the coma. In fact, hardly any coma at all. No bursts of dust. No fan-shaped jets. No debris plume that could explain a shove in one specific direction. The object moved like a craft executing a planned maneuver, but looked, in all the usual wavelengths, like a quiet, almost dormant lump. This was not the first time 3I Atlas had refused to play by comet rules. Weeks earlier, an amateur solar observer in Chile had captured a curious image. Against the glare of the sun, there was a small, dark core and a faint cone-shaped puff extending toward the sun, not away from it. It looked like an exhaust plume aimed straight into the star. At the time, the observer assumed it was an imaging artifact, a trick of motion blur, maybe a solar flare reflection. They filed it and moved on. Only when the November trajectory anomaly hit did that image come back under the microscope. Comet scientists know a phenomenon called an anti-tail, where viewing geometry can make a dust structure appear to point forward along the orbit. But anti-tails still live inside a large, dusty environment. They need a bright coma, lots of scattered particles, and a specific alignment between Earth, Sun, and the comet. When analysts ran a simulation for the Chile observation, the geometry did not match an anti-tail. Worse, the shape in the image was wrong for a natural plume. It did not billow and widen like a vented cloud. It held a tight taper, almost like something had squeezed the flow into a narrow beam. When the data was pushed through software, usually used to analyze rocket exhaust, the cone behaved like what engineers call a collimated emission, a directed outflow. That does not prove a thruster. It does, however, put 3I Atlas in a small and strange box. Either it has some completely new kind of natural venting that just happens to mimic engineered exhaust, or something is shaping its outflow from the inside. Add that to the November silence. No tail where there should be a tail. No heat where there should be heat. No coma flare where there should be chaos. Yet the orbit bends with alarming precision toward a narrow slice of space that Earth will soon cross. In basic physics, if you see motion, you go hunting for force. With comets, you normally do not have to hunt very hard. The forces announce themselves in every glowing photograph. In this case, the force is invisible. The turn appears, but the usual fingerprints are missing. That leaves us standing in an uncomfortable doorway. On one side, a natural explanation that keeps breaking its own rules. On the other, a controlled system, a shell or platform that moves itself without spraying visible jets into space. For now, the official story still calls 3I Atlas a comet, but the list of things it refuses to do like a comet is getting longer. Inside the European Space Operations Center, most deviations have boring explanations. Solar wind gusts, telescope pointing quirks, software that slips by a decimal. The default instinct is always to blame the tools before blaming the universe. So when the first alert tied to 3I Atlas fired in the early hours of November 22nd, no one sprinted to a microphone. Not yet. For about half an hour after Felix first flagged the anomaly, the team did what orbit analysts always do. They waited to see if the numbers would relax back into line. Most oddities do, but by around 5:37 Universal Time, the deviation had not only held, it had sharpened. The fit to a simple outbound curve was gone. The new trajectory hugged the updated vector with uncomfortable precision. At 5:42, an automated threshold was crossed. Inside the secure network, a quiet protocol triggered. 3i Atlas tripped from routine tracking into a higher category. Not because anyone saw a dramatic flare in the sky, but because the math refused to behave. The system generated an internal alert and sent it to a small list of duty coordinators with one message inside the jargon. This object had just broken containment. Containment here did not mean a physical box. It meant a conceptual box. Up until that moment, 3i Atlas lived in the same category as other unbound interstellar visitors. Interesting, exotic, ultimately harmless. The new numbers did not fit that box anymore. They showed deceleration. They showed alignment. They suggested something more deliberate than the graceful mechanics of pure gravity. Behind the scenes, the database began to shift. Telemetry folders with names like ephemeris modeling and post-Mars orbital decay, which had been available to a broad pool of researchers, started to vanish from shared drives. Access requests that had been green a day earlier began to return red warnings. 3 scientists lost access in real time while they were logged in. 2 of them were working on their own independent trajectory predictions when their screens froze. One postdoctoral researcher in Portugal took a screenshot of his sudden access denial and posted it to a social media platform. The post did not last long. Within a couple of hours, it disappeared, like the data stream it described. But by then, copies of the image had already spread through private chat rooms and email chains connecting professional astronomers and serious amateurs. The quiet clampdown was visible, even if the reason was not. At the same time, observatories across Europe began receiving new tasking instructions. Instead of simple optical tracking, several were told to pivot to thermal residual analysis. That method is usually reserved for failed satellites or stealthy hardware. It looks for the faint warmth of a cooling structure rather than the bright flare of reflected sunlight. That is not how anyone usually studies a comet. Yet 3i Atlas was suddenly being treated like possible space hardware. By about 6:12 Universal Time, a second wave of changes hit the internal systems. The object's label in the coordination software was rewritten as Capture Candidate, Orbital Stabilization, Pending. Those 4 words rippled through scheduling algorithms. Telescopes that had been booked for deep-field galaxy surveys were bumped. 3i Atlas rose in priority, nudging aside other programs that had taken months to arrange. Quietly, the object had been promoted from curiosity to concern. The term capture carries a specific weight. For something on an originally hyperbolic path to become captive to a star or planet, it must lose energy. It has to shed speed or be acted on by a strong external field. None of the usual suspects were present. There had been no major solar flare in the right window. Mars, which 3i Atlas had already passed, was not massive enough at that distance to provide such a clean break. No wake of gas or dust had been seen that could hint at an invisible rocket push. And yet the trajectory now looked like that of a body being coaxed into a more stable relationship with the inner solar system. The reaction was not limited to Europe. Those internal updates at the European agency triggered a handoff to the Deep Space Antenna Network. Antennas that normally spend their days talking to probes around Mars, Jupiter, and beyond were tasked with intermittent radar-style pings along the new path of 3i Atlas. These were not broad, lazy sweeps. They were tight, precise pulses of energy aimed along a well-defined line. The same tools used to measure tiny changes in speed and spin in. Fast-moving artificial objects were now being turned on something, still officially described as a comet. In public, none of this existed. The European agency website still listed 3i Atlas under a calm heading for recent interstellar passers-by. The publicly visible trajectory plots remained unchanged for hours, still showing the original safe outbound arc. No notice appeared to say that internally, the object had been moved onto encrypted channels, usually reserved for active planetary defense scenarios. Inside those secure channels, the tone shifted. What had started as a scientific puzzle was now being discussed in the language of strategy, capture windows, energy loss events, stabilization options. People whose normal job is to model asteroid deflection scenarios or track space debris were being pulled into threads about an interstellar visitor that was supposed to have nothing to do with Earth. From the outside, that day looked like any other day in space science. A quiet, calendar entry for an upcoming press briefing. Some updated plots on tracking sites. Nothing for the average person to worry about. Inside, 3i Atlas had crossed an invisible line. It was no longer just something we were measuring. It was something that systems built for defense were now watching as if it might be making plans of its own. If you want a single image that captures everything strange about 3i Atlas, it is not a glossy render from a space agency. It is a slightly noisy frame from a backyard solar telescope in Chile. No dramatic colors, no cinematic flair, just a small dark speck near the sun and a faint cone of light pointing in the one direction comet tails are not supposed to point. Straight at the star itself. The observer who caught it was not hunting for alien spacecraft. They were testing filters, logging solar activity, and happened to pick up the interstellar object near the edge of their field. In the raw frame, 3i Atlas is tiny. The cone is even smaller. At first glance, it looks like a smear, the kind of imperfection you would expect from atmosphere or motion blur, the kind of thing you delete without thinking. For a few days, that is exactly what happened. The image was posted, briefly discussed on an astronomy forum, then largely ignored. The observer assumed it was an artifact, maybe a sensor streak, maybe a ghost from a flare. It did not fit any tidy category, so it was treated as a glitch. Only after the November trajectory change did people scroll back and look again. When comet specialists revisited that frame, they did what they always do. They tried to fit it into known phenomena. The first candidate was the anti-tail illusion, a trick of perspective that sometimes makes a dust structure appear to point forward along the orbit. It happens when Earth crosses the orbital plane of a comet and looks back along the line of particles trailing behind it. From the right angle, that backward trail seems to stick out ahead. Anti-tails are rare, but well understood. They still require a bright coma and dust-rich environment. They still involve material being pushed away from the sun by radiation and wind. The apparent forward angle is entirely from our point of view, not because the dust is actually driving into the solar wind. So, analysts ran the numbers for the Chile observation. They reconstructed the geometry of Earth, Sun, and 3i Atlas at that exact time. They modeled where a true anti-tail would appear in the frame. The simulation did not match. The angle was wrong. The length was wrong. The structure in the photo cut across the expected dust plane instead of lining up with it. Next, they looked at the shape itself. Natural comet jets are messy fountains. They burst through cracks and vents, expanding rapidly as they enter vacuum. By the time we see them from Earth, they are wide and diffuse, more like a spray from a shaken soda bottle than a tight beam. The cone in the Chile image was different. It stayed narrow far longer than it should have. Its edges were surprisingly well defined. When the data was pushed through plume analysis tools normally used by aerospace engineers, the cone behaved more like a directed exhaust than like a boiling vent. The software flagged the profile as consistent with what propulsion experts call collimated emission. That phrase describes a flow that has been shaped, squeezed by a nozzle or field, so that it holds together instead of exploding outward in all directions. None of this proves that we are looking at a rocket engine, but it does put the event in unfamiliar territory. To keep a gas flow that tight over that distance, you need either an extremely special natural environment or some kind of guiding structure. There was no obvious environment. There was just deep space and a small, stubborn object. The timing made the frame even more unsettling. The Chile observation was recorded days before 3i Atlas reached its closest point to the Sunday. It shows the forward cone, then no repeats. Later images show no steady jet, no continuous plume, no long-lived structure in that direction. It is as if something fired once, briefly, then went quiet. When analysts lined up the timeline, the pieces formed a rough sketch, a short, forward-pointing cone event, before perihelion. Then, weeks later, a clean course correction that nudged the object toward Earth's orbital plane, executed with no visible outgassing at the moment of the shift. It is impossible to prove a direct link between the cone and the vector change. Yet, the idea that we glimpse the trace of an earlier maneuver is hard to ignore. If we imagine 3i Atlas as a controlled platform, that cone looks like a burn, a thrust toward the sun to adjust speed or angle. In spacecraft design, firing toward the central body can tighten or reshape an orbit. A brief inward push can set up a later, more subtle path change farther out. That is exactly what appears to have happened. An early nudge, then a later alignment with Earth's future position. If we stick with the comet model, the picture becomes far more strained. We have to accept an outburst that somehow shoots material straight into the solar wind, stays narrow in a way natural jets do not, shows up only once, and happens to precede a series of moves that look like deliberate navigation. Each puzzle piece on its own might be explainable. Together, they start to feel like a pattern. In science, single images can mislead. One frame does not make a theory. Yet that small cone pointing at the sun has become a kind of icon in the quiet debates around 3i Atlas. For some, it is the first visible scar of an engine we do not understand. For others, it is a stubborn glitch that refuses to be filed away as a trick of light. What is clear is this. Whatever that cone was, it broke more than one rule at once. It ignored the usual direction of comet tails. It ignored the usual shape of natural plumes. It appeared once, then vanished. And as the object now moves along a path that seems increasingly tailored to Earth, that brief, bright signature hangs over the story like graffiti on otherwise smooth metal. Someone, or something, might have left a streak of intent in the sky. The James Webb Space Telescope was not built to watch things move. It was built for stillness, for ancient starlight, for galaxies that do not seem to change on any human timescale. Yet in late October, one of its calibration targets was not a galaxy at all. It was the faint blur of 3i Atlas, a side project, a filler target, something to point at while the main science marched on. Until someone noticed that the blur was not actually still, it was beating. The data that changed everything began as a routine check. Analysts at the Space Telescope Science Institute were reviewing mid-infrared scans of 3i Atlas, taken around 35 micron wavelengths. These images were meant to test the consistency of Webb's sensor grid. They looked for bad pixels, drift, noise. What they found instead was rhythm. When they plotted brightness over time, the line did not wander up and down the way a natural coma usually does. It rose and fell in a smooth, repeating wave. The pulse completed one full rise and fall every 11.2 hours, with less than 1% variation from cycle to cycle. For a natural object shedding dust and gas in the harsh environment near the sun, that level of precision is strange. At first, the team tried to explain it as rotation. Maybe 3i Atlas was slowly spinning, exposing brighter regions at regular angles. That is common. Tumbling ice bodies often show repeating light curves as different faces turn toward us. But rotation signatures have quirks. They wobble over time. They drift as jets open and close, as the surface erodes, as the spin axis precesses. The signal from 3i Atlas did not drift. When the analysts mapped the pulse into a brightness amplitude chart, they saw something else layered on top. Every fifth cycle, a smaller peak appeared exactly halfway between the main pulses. A harmonic. In musical language, it was like a second note riding on top of the first, at a perfect octave. In physical terms, it looked like frequency doubling. One stable beat with a second beat precisely locked between the steps. Natural comet behavior is messy. Outgassing eruptions are stochastic, which means they are random and noisy. Surface glints from ice patches come and go. Jet activity depends on crack growth and sunlight angle. Yet this light curve from 3i Atlas had the eerie regularity of a metronome. No extra spikes. No missing beats. Just that 11.2-hour rhythm and the faint harmonic whispering in between. The next question was where the pulse came from. Was it simply a trick of reflectivity on the surface, or something deeper? To find out, researchers compared the mid-infrared data with near-infrared and longer thermal readings. If the effect was just a shiny patch turning toward Webb, it would show up strongly at some wavelengths and weakly at others. Instead, the same rise and fall appeared across multiple bands at the same moments. That meant the change was not just skin deep. The emission looked volumetric, as if the entire coma, or at least a large region around the nucleus, was brightening and dimming in unison. The energy source seemed to be inside the object, not just bouncing off its crust. Around the same time, ground-based observatories began reprocessing their own data. The Las Campanas Observatory in Chile had recorded subtle brightening events from 3I Atlas days earlier, but had treated them as noise. After seeing the Webb report, they went back and stacked their exposures with the pulse period in mind. The same 11.2-hour cycle emerged. Amateur astronomers were pulled into the story as well. In New Zealand, a high-altitude observer, experimenting with green and near-ultraviolet filters, had captured a sequence of 30-second frames over a 6-hour run. When they animated the images, the coma seemed to swell and relax, swelling again on the same schedule reported by Webb. Expansion, contraction, expansion, contraction. Not explosive flares, not random jets. A slow, controlled breathing. Stacked exposures from Australia told a similar tale. The outer boundary of the coma shifted by a few percent in radius between minimum and maximum phases. On paper, a change of about 5% does not sound dramatic. In physical space, around an interstellar object, that translates to thousands of kilometers of atmosphere, gently inflating and deflating in sync with the light rhythm. Astrophysicists scrambled to find a natural process that could do this. One idea was internal resonance. In some icy bodies, heat from the sun can build pressure under the surface. Gas pockets expand and collapse, releasing in timed bursts. But those systems are typically messy, driven by fractures and weak points. They do not produce perfectly smooth waves that ignore external events. Another possibility was magnetic breathing. A conductive object moving through the solar wind can experience changing electromagnetic forces. Plasma fields can compress and rebound, sometimes creating rhythm in charged environments. Yet those rhythms respond directly to solar conditions. Flares, wind speed changes, and magnetic storms all leave fingerprints. The pulses from 3I Atlas did not seem to care about any of that. They kept time through perihelion, through solar variability, through the later trajectory shift toward Earth. The consistency of the beat suggested something that natural systems rarely show on their own: memory. Biological or mechanical, memory implies a pattern that persists regardless of noise. In internal reports shared with only a small group of cross-agency teams, one phrase began to appear more often. Not heartbeat, which feels too biological, but breath signature. An engineered or emergent rhythm that looked like an inhale and exhale on cosmic scale. Of course, official language stayed cautious. The final summary circulated between agencies used careful phrases. Periodic luminosity remains unidentified. System stability exceeds that of known natural rotators. Further modeling required. There was no claim of a machine, no mention of intent, only the data, and the uncomfortable way it lined up with itself, over and over again. Outside those circles, independent researchers started to plot their own charts. Shared graphs on private forums showed the same 11.2-hour slope traced in different colors from different telescopes. Each dataset had its quirks, different noise levels, different baselines. Yet when the peaks were lined up, they marched together like the steps of a single, hidden mechanism turning in the dark. The real unease came when people overlaid this breathing pattern with the timeline of events. The pulses were present before the vector change. They continued after it. The coma expanded and contracted gently even as the trajectory bent toward Earth's orbital plane. It was as if whatever was inside 3i Atlas had its own schedule, and the maneuver had been timed to fit inside that schedule. We still do not know what is causing that rhythm. It might one day slide neatly into a new branch of comet physics, some exotic resonance, a kind of thermal lung no one has seen before. Or it might be exactly what it looks like to the human mind. A steady, patient breath from something that is not just falling through our solar system, but operating within it. For now, all we can say with certainty is simple and strange. 3i Atlas is not only moving, it is keeping time. While everyone was staring at the orbit, a quieter clue slipped in through the spectrum. It did not look dramatic. No glowing image. No eerie silhouette. Just a spike in a graph from an instrument on the ExoMars trace gas orbiter. A single sharp line that should not have been there on its own. Nickel without iron. In space, that pairing is like seeing smoke without fire. On November 21st, ExoMars was not even supposed to be doing anything special with 3i Atlas. One of its side-mounted spectrometers was running a routine sweep across the region where the object had last been seen, mainly to calibrate background noise and tune its filters. Space is full of random flashes. Cosmic rays, solar interference, electronic crosstalk. Most of the time, odd spikes get thrown out. When the data was processed the next day, just hours before the confirmed trajectory shift, that spike refused to be thrown out. It appeared again, in the same narrow band of the infrared spectrum. This time, when scientists decomposed the signal, they found a clean, symmetrical emission line centered around a wavelength of about 9 microns. That wavelength corresponded to a very specific molecular vibration, not of water, not of carbon dioxide, not of dusty silicates, of nickel vapor. Nickel is not rare in the universe. It is forged in supernovae, lives in the cores of planets, and shows up in meteorites all the time. But almost everywhere we find nickel in space, we find iron sitting next to it. The two metals are like siblings. They condense together in the hot, dense cores of asteroids and protoplanets. When those bodies are shattered, they travel as a pair. In spectral lines, iron is usually the louder voice. In the ExoMars data from 3i Atlas, iron was missing. Not weak, not buried under noise, just not there. Only nickel spoke. That absence is what made scientists sit up. Because for nickel to show up alone in gas form, above a supposedly natural object, something odd has to have happened to its iron partner. Either the iron was somehow removed or it had already been boiled away earlier, leaving nickel behind. Both options are troubling. If iron was stripped out, that suggests a selective process. On Earth, when we want nickel without iron, we use industry. High-temperature smelting, repeated heating and cooling, electromagnetic sorting, complex chains of machinery built to separate and purify. These are not gentle accidents, they are deliberate. If instead, the iron had boiled away earlier, that implies temperatures high enough to vaporize one metal and not the other in a controlled way, without leaving chaotic thermal scars in the surrounding gas. Yet when researchers checked the thermal profile of the coma, they saw no corresponding heat spike, no flaring, no hot plume, no obvious furnace. The nickel vapor was simply there, hanging in the spectrum, with no visible engine making it. The shape of the line made the puzzle sharper. It was narrow and symmetric, meaning the nickel atoms were not locked into mineral grains or complex crystals. They were free, unbound, moving as a gas. Free-floating metals in gas form require extraordinary conditions. Either you pass through an atmosphere at blistering speed, like a satellite re-entering Earth, or you subject the material to focused energy on purpose. Someone remembered an old dataset from 2018 when a fragment of a dead satellite fell back into our atmosphere. An infrared weather satellite caught the re-entry. Its spectrum showed a nickel-dominated line, very similar to the one now seen near 3i Atlas, produced as high-performance alloys burned and peeled away under controlled descent. That comparison was not proof of anything, but it was a hint. Could 3i Atlas be carrying something like a heat shield? A skin that sheds or vaporizes in a way designed to manage temperature and radiation? If so, the nickel could be part of that structure, a radiative layer that is slowly eroding in a way that hides the underlying material. Internal memos at the European Southern Observatory began quietly using a new word in their drafts: industrial. They did not publish it. They certainly did not tweet it. But it appeared. There were other, more conservative ideas. Maybe the object had once been part of a planetary core that was stripped in a violent event, leaving a nickel-rich fragment with unusual chemistry. Maybe a past explosion had preferentially thrown iron away. Yet even those scenarios felt strained when weighed against the rest of the behavior. No tail, precise course changes, breath like pulses, forward cones that look like engines, and now, a whiff of refined metal. The ExoMars team knew their detection would be controversial, so they checked everything. Sensor calibration, dark frames, background subtraction. The line stayed put. Other instruments, on other platforms, began to see the same signature when they looked for it. Narrow, clean nickel. Still no iron. The odds of a glitch, repeating across systems and observatories, dropped with each confirmation. After this, observation plans changed. ExoMars updated its filters. New bands were added to track the nickel line over time. Data release schedules were quietly delayed. In at least one internal briefing, 3I Atlas was described not only as chemically anomalous, but as a possible repository of processed material. That is a polite way of saying this. We might be looking at metal that has been through a factory, not just through a star. Standing alone, a nickel-only line in a spectrum might be a curiosity and nothing more. But in the context of an object that bends its orbit without visible thrust, pulses with mechanical regularity, seems to conceal itself from Doppler radar, and now appears to be bleeding pure metal gas, it starts to feel like part of a design. A skin, a shield, a layer meant to take the heat while something else inside remains hidden and cold. We do not yet know whether that interpretation is correct. The universe has surprised us before with natural processes that impersonate technology. But until someone can show a clean, natural path to nickel without iron, floating above a silent, cold object on an impossible trajectory, the industrial shadow hanging over 3I Atlas will only grow darker. Some of the most expensive instruments on Earth were struggling to understand 3I Atlas, yet one of the clearest glimpses of what it might be came from a backyard in Australia, not from a billion-dollar observatory. From a modified amateur telescope pointed at the edge of the sun by someone who was not even trying to track the object at the time, the user went by a handle on a small astronomy forum. On the morning of November 22nd, at about 0713 Universal Time, they uploaded a short stacked frame video. The caption was simple and confident. They had reacquired the interstellar object moving cleanly through the expected coordinates, and in their words, this was no comet. The footage ran for about 15 seconds. It was assembled from a burst of images taken through narrowband filters using a heavily tweaked Celestron Edge telescope. The setup was designed to cut through solar glare and pick out faint structures close to the sunday. Most nights, it hunted for sunspots, prominences, and odd reflections. On this morning, it caught something else. Frame by frame, the clip shows a star field washed in low-contrast haze near the limb of the sunday. Then, in the center of the field, a tiny shape glides through. Not a fuzzy ball, not a glowing puff, a distinct form with length, elongated, more like a fin or a spike than a round nucleus wrapped in mist. There is no visible coma surrounding it. No tail stretching away from the sunday, no halo from outgassed dust. Instead, the object presents as a slim rod, with a brightness gradient that remains remarkably even from end to end. Natural bodies, especially icy ones, scatter light unevenly. As they tumble, one side flares, another dims. Here, the brightness hardly changes as it crosses the sensor. At the end of the clip, background stars drift slightly as expected from Earth's rotation and the tracking pattern of the mount. Against that gentle drift, 3i Atlas cuts across the field with a motion that looks strangely disciplined. No wobble, no jitter, no sign that jets or irregular spin are tugging at its path. Just a smooth, directionally locked glide along a line. At first, only a few forum regulars noticed. They commented on the shape, on the lack of fuzz, on how much more like a spacecraft it looked than the usual comets, which tend to bloom out into soft blobs in stacked exposures. The thread might have ended there if someone had not tried an overlay experiment. One user pulled the latest public trajectory data from a NASA ephemeris tool, then plotted the expected projected path of 3i Atlas across the sky at that exact time and location. When they overlaid this line onto the stacked frames, the result was disturbing. The object followed the updated heading perfectly. Pixel perfect, as one analyst later described it. This would already be impressive if the public trajectory had been up to date. It was not. The line in the video matched the revised internal path that accounted for the recent vector shift, not the older hyperbolic outbound curve still shown on public sites. In other words, the backyard video was following a script that had not yet been officially published. When other forum members pressed the original poster on how they knew where to point their telescope, the answer was modest. They claimed they had not been tracking 3i Atlas at all. They had been watching sunspot interference patterns and noticed a moving speck near the predicted region, then refined their aim. Maybe that was true. Maybe it was luck. Either way, they had filmed the object cleanly, before most large instruments had reacted to the new orbit. News of the clip moved quickly through private channels. Amateur astronomy groups on encrypted messaging apps shared mirrors of the file. Professional astronomers with an interest in the object downloaded it quietly and ran their own frame-by-frame checks. A specialist in optical calibration for a commercial satellite company examined the footage with the same tools used to study space hardware. Their assessment, shared off the record, was blunt. This did not behave like a rock. The consistent reflectivity, the lack of rolling light curves, the absence of a fuzzy halo, and the stable vector all pointed to something else entirely. In their view, the object looked more like a platform, a structure that maintained its orientation deliberately rather than a natural fragment tumbling unchecked. Once the video began circulating, observers in other parts of the world tried to repeat the capture. Astronomers in New Zealand, Argentina, and the Canary Islands pointed their scopes to the same patch of sky, using similar filters. Most saw nothing. The glare was too strong, or the object too faint against the noise. A few, however, caught brief streaks that, when stacked, showed a familiar signature. A linear shadow cutting across the background with almost mathematical grace. Again, no cotton ball blur, no ragged outline, just a thin, steady mark, as if a needle were being dragged across the stars. The more those images piled up, the harder it became to sustain the idea that 3i Atlas was just a lumpy chunk of ice and rock. We have seen plenty of those. They tumble, they shimmer, they trail gas. They almost never present as neat rods holding a fixed attitude while making precise course corrections in line with hidden orbital updates. Inside official agencies, there was still no comment. Websites continued to list 3i Atlas under interstellar comets. Press offices kept quiet. But within the blended community of professionals and serious amateurs, a new informal consensus began to crystallize. Whatever we are tracking is not behaving like a comet at all. It moves like something that was built to move. It holds its pose like a craft with attitude control. It flies along a path that seems to have been calculated in advance, then fine-tuned as it goes. And the first clear footage that hinted at this did not come from a flagship observatory, but from a backyard telescope, a patient observer, and a 15-second clip that the world almost scrolled past. On the radio charts, space is rarely silent. Even empty regions fuzz with background hiss and faint echoes from dust and distant objects. That is why the engineers at the Goldstone Deep Space Complex in California expected at least some response when they turned their dishes toward 3i Atlas on November 22nd. They were not looking for a message. They were just listening for motion. What they got instead was a flat line so clean it felt like an answer. The scan they ran was not aggressive. No high-power radar ping. No loud shout into the void. It was a passive Doppler listen, using natural radio emissions and reflected signals to measure how the object was moving. The principle behind it is simple. When something travels toward or away from a receiver, the waves it reflects shift slightly in frequency. That shift is how we measure speed and spin for asteroids, comets, and even bits of drifting space junk. Normally, even very dark objects give you something to work with. A faint blip, a smeared echo, some kind of distortion in the background that says there is a body there, sliding through the field. On that November morning, when Goldstone pointed its antennas at the updated coordinates of 3i Atlas, they saw none of that. No Doppler shift, no echo, no measurable scatter. It was as if the object were not there at all. Engineers do not trust silence. Their first instinct was to blame the hardware. They ran diagnostics on the receivers, checked for local interference, and verified atmospheric conditions. Everything checked out. Just hours earlier, the same system had picked up a clear return from a low Earth object. The instruments were awake and healthy, so they tried again. Different timing, same region, same result. Nothing. You might expect a comet to be a difficult target for radar, and that is true. Cometary material can be porous and dusty, scattering signals in messy ways, but messy is still something. Even the darkest carbon-rich asteroids, spinning fast and soaking up light, send back a noisy but usable fingerprint in radio bands. 3i Atlas was not noisy. It was null. Inside the team, one possibility came up quickly. Maybe the surface was coated in an ultra-absorbent material, something like the engineered carbon structures on Earth that swallow almost all visible light. Artists and militaries both know that black coatings can hide shape and texture. Extend that concept into radio frequencies, and you could imagine a skin that drinks radar, leaving almost no reflection. The problem is that in nature, nothing is perfect. Even the best human-made absorber in a lab does not erase a signal completely in all directions and frequencies. There is always a residue. There is always a little noise. What Goldstone saw from 3i Atlas looked like active cancellation instead of simple absorption. That is a technique already explored in stealth technology on Earth, where aircraft emit carefully tuned signals to interfere with the radar that hits them. They do not just hide in darkness. They fight back with physics. Another theory was even stranger. What if, at the right wavelengths, the object was functionally transparent, made of a material or surrounded by a field that lets radio waves pass through as if it were not solid? That would also produce silence. But if the whole thing were transparent in that way, you would expect it to vanish across the spectrum. 3i Atlas does not. We can see it optically. We can measure its thermal glow. Its invisibility seems to apply only to the very tools used to weigh and time its motion. That selectiveness is what made the Doppler void so unsettling. Nature can be harsh, but it is rarely selective in such a tidy way. Dust is dusty to everyone. Metal reflects everything to some degree. Gas clouds scatter regardless of who is looking. When an object shows up clearly in visible and infrared light but behaves like a ghost to radio tracking, it begins to feel like it is choosing which questions it will allow us to ask. The Goldstone team logged the result in 2 different tones. In the public-facing archive, the event was filed with neutral language, non-reflective object, Doppler inconclusive. On internal channels, the wording was sharper. Some called it the cleanest Doppler void they had ever seen. That is not a phrase anyone wanted to attach to an interstellar visitor, now gliding toward Earth's orbital lane. From a navigation standpoint, this silence is more than a curiosity. The global network of deep space antennas relies on Doppler measurements to refine trajectories, infer mass, and monitor rotation. If 3i Atlas can slip through that net, it undermines one of our main ways of keeping track of fast movers in the inner solar system. It is not just hiding in the dark, it is hiding in the equations. Combine that with its other behavior, and a pattern starts to emerge. An object that changes course with no visible thrust, that sheds nickel vapor with no iron, that pulses in light like a metronome. That appears as a rod holding strict orientation in backyard videos. And when we switch to the instruments that should reveal its true momentum, it simply vanishes from the readout. There may yet be a natural explanation that ties all of these threads together. Some exotic composition, some new kind of surface structure, some interaction with the solar wind that mimics active stealth. For now, though, the simplest description is the most unnerving. Whatever 3i Atlas is, it behaves as if it does not want us to know how fast it is really moving, how it is spinning, or how massive it might be. On the morning when Goldstone listened and heard almost nothing, 3i Atlas was already on its new Earth-crossing heading. We could see it. We could feel its presence in the changing orbit models. Yet when we asked one of our most trusted tools to trace its motion directly, the universe gave us a blank. The silence was not empty. It was shaped. And that shape looked a lot like a choice. Up to this point, most of the weirdness around 3i Atlas lived in the sky and in the math. Strange pulses, impossible cones, a trajectory that bent toward Earth. But on November 22nd, something else shifted that you and I can recognize instantly. The data stream itself started to go dark. Not because a telescope broke, because someone turned the tap. At 9:06 Universal Time, just under 4 hours after, the vector change was first logged. The ExoMars Trace Gas Orbiter was still doing its job. Its instruments were sweeping the region where 3i Atlas had been, pulling down infrared and ultraviolet readings that had already revealed pure nickel in the coma. The telemetry link back to Earth was healthy. Power levels looked normal. Then the science data stopped. It did not stutter or fade. It did not throw obvious errors. The feed just went quiet for the instruments that mattered most. The connection to the spacecraft remained green on the consoles. Engineers could still see status lights for attitude control, power, and health checks. Yet the raw observation channel flattened. Silence flowed through the line where spectra and thermal maps should have been. At first, teams on the ground assumed it was a technical headache, a bottleneck in a relay, a disk problem at a ground station. Spacecraft go into safe modes. Downlinks get throttled. The usual explanation is always a glitch, but this silence lasted for a very precise interval. 4 hours and 16 minutes. When the stream finally resumed, the log showed something stranger than noise. 2 entire data files were missing. They were not flagged as damaged. They were not marked for reprocessing. They simply did not arrive. Their timestamps lined up eerily well with the window during which 3i Atlas completed its deceleration and settled into its new Earth-aligned arc. According to the original observation plan, those files should have contained high-resolution spectral images and thermal maps from instruments facing the part of space where the object was moving. Instead, a placeholder tag appeared in the archive. Data under review. Integrity check pending. That placeholder stayed unchanged for 3 days. During that time, outside researchers who had been promised prompt access to ExoMars readings began asking questions. Requests for clarification brought back vague replies. Operational diagnostics, bandwidth management, telemetry prioritization, all technically plausible. None answering the simple question you would probably ask too: where is the data? Inside the European Space Agency, internal message boards told a sharper story. One anonymous post from someone in the Planetary Science Division claimed the downlink had been interrupted on purpose. Not a failure, a command. Log files from the relay system suggested that the transfer of science packets from ExoMars had been manually suspended, then manually resumed. Only Mission Control in Darmstadt, or Central Command, at the main agency hub has that authority, which means a human being approved those missing minutes and hours. Why would anyone pause the one set of eyes that happened to be looking straight at an interstellar object while it changed speed and slipped into an Earth-crossing path. No official has stepped forward with an answer. The public-facing explanation is still wrapped in technical phrases. Yet, behind the jargon, one idea has taken root among scientists who have seen the internal logs. Temporal containment. Not just data suppression, but delay. Holding back information until someone decides how or whether to share it. That same day, another signal of containment appeared, this time in full view of the public. A joint press briefing between NASA and the European agency had been scheduled for late morning. The event had been on calendars for a week, advertised as an update on the trajectory of 3I Atlas and the so-called Interstellar window. Journalists had submitted questions in advance. Background notes had gone out. Panelists from the Jet Propulsion Laboratory and the Operations Center were booked. Then, with no warning, the event vanished. On the NASA live stream page, the placeholder was removed with a simple note that the broadcast had been taken down by the host. On the European site, the listing remained, now marked as unavailable due to an internal scheduling conflict. No new date, no substitute announcement, just a polite, blank wall. For reporters who cover space, this felt wrong. Technical glitches happen all the time, but briefings are usually postponed, not erased. Several science journalists filed information requests that same day, asking for emails, meeting minutes, and draft slides related to the canceled event. Weeks later, no full answers have surfaced. Behind the scenes, a few agency insiders sent the same short message to trusted contacts. The briefing was pulled above our level. You do not need to be a conspiracy theorist to see what that implies. Only national-level oversight bodies, often with defense ties, have the authority to override a joint international science briefing at the last minute. The last time something similar happened on this scale, it involved a capsule crash that scattered precious samples across a desert. This time, there was no wreck, no fireball, no hardware failure. Only revised orbit models, and a growing list of anomalies around a silent object from interstellar space. In the days that followed, another pattern emerged. Several of the scientists who had been scheduled to appear on stage at the canceled briefing quietly withdrew from upcoming conference talks in December. Abstracts that had been accepted were marked as withdrawn. Public-facing social media accounts that usually overflowed with plots and telescope photos went quiet. No farewell posts. They simply stopped commenting on 3I Atlas at all. Meanwhile, the gap left by the missing official data began to fill with something else. Amateur astronomers shared their tracking videos. Independent labs published their own pulse charts and coma breathing analyses. Forums lit up with overlays of backyard footage and leaked internal orbit projections. 3I Atlas kept moving. The sky refused to pause. The only real silence lived in the offices that had the best view. In astronomy, silence from an instrument usually means hardware trouble, dust on a mirror, a dead detector, a network outage. What happened around 3I Atlas on November 22nd was different. The telescope did not fail. The orbiter did not die. The teams on the ground did not suddenly forget how to downlink files. Files were skipped, briefings were canceled, voices fell quiet. We may eventually see those missing spectra. They might be released quietly, folded into a dense technical paper months from now, after the public has moved on. They might arrive redacted, or with careful language that turns sharp features into tidy footnotes. Or they may never be fully acknowledged. Whatever happens, the timestamps will not change. At the exact moment an interstellar object slowed down, turned, and locked its path into the same slice of space Earth is heading toward. Our official eyes closed, and the people who closed them declined to explain why. In orbital mechanics, the present is almost boring. The real drama lives in the future. Where an object is right now matters far less than where it will be and when it will arrive there. A few degrees of angle or a few seconds of timing can turn a harmless flyby into a close shave, or a close shave into a capture. When analysts pushed the latest data for 3i Atlas forward on the 22nd of November, that future suddenly tightened around one specific world: ours. The models that came out of the European Navigation Office that day showed something unsettlingly precise. 3i Atlas was no longer just crossing the broad disk of Earth's orbit. It was sinking into sync with it. Project the path 38 days ahead, and the object passed through the exact region of space that Earth itself would occupy at that time. Not a direct bullseye impact, but not a casual miss either. A crossing corridor only a few 100,000 kilometers wide in a solar system that is mostly empty. To hit that kind of corridor by accident, with an interstellar visitor, is extremely unlikely. The solar system is a huge three-dimensional target range. Planets move fast. Earth alone races around the Sun at roughly 30 kilometers per second. Most passing bodies slice through the orbital paths at random angles and move on. Only two processes are usually invoked when you see repeated close alignment: natural resonance over long timescales or deliberate correction. 3i Atlas did not have the time to fall into resonance. It is not a long-term resident of the system. It came in hot on a hyperbolic track, past Mars and toward the Sun, then out again. For it to end up passing through the same slice of space as Earth at almost the same moment, something had to change its speed and angle along the way, shaving down the missed distance until the numbers lined up. When engineers ran the clock backward, they found something even more telling. To achieve the current alignment, the object would have had to start making tiny corrections at least 11 days earlier, back when it was still approaching the Sun and first feeling serious solar heating. That means the maneuver on November 22nd was not a spontaneous lurch. It was the last step in a planned sequence. A final nudge to lock in a window. In mission design for spacecraft, there is a term for this kind of opportunity: a capture window. A narrow span of time and geometry where the difference in velocity between two bodies becomes small enough that you can enter orbit or execute a controlled flyby using relatively little energy. We do this when we send probes to Mars or Jupiter. We wait until the capture window opens. Then we burn our engines to slip into a trajectory that arrives at just the right place, at just the right moment. The modeling teams at NASA and the European Agency quietly began to use similar language for 3i Atlas. This was no longer just an outbound comet path. It looked like an approach. The spread of possible future positions, the uncertainty, cloud, did not widen with time the way it normally does for a poorly understood object. It narrowed. Each new data point from telescopes and tracking stations made the predicted intersection corridor thinner and more specific, as if the object were lining up for descent. This brings us to the question that no one from any agency has yet asked in public. Why would an interstellar object align so precisely with the moving orbit of a habitable planet unless that planet was part of the plan? The core facts are stark. An object from outside the solar system has changed its trajectory. It has slowed relative to a simple hyperbolic escape. It is now on a path that converges with Earth's future position with the precision we normally associate with guided vehicles. Inside the scientific community, three main theories have emerged. None have been officially endorsed. All are whispered. The first is the most comforting: passive observation. In this scenario, 3i Atlas is a long-lived probe launched millions of years ago by some distant civilization, programmed to skim habitable worlds. It does not care about us specifically. It is following a pre-written tour of planets that fall within certain temperature and chemistry ranges. The recent vector shifts would then be parts of that script, adjusted for real-world conditions but fundamentally pre-planned. There are problems with this calm picture. Stealthy behavior is unnecessary for a purely passive scout. A machine designed only to gather data does not need to suppress its Doppler signature or erase radar echoes. It does not need to hide its mass from the very instruments that could tell us whether it is dangerous. It also does not need breath like light pulses and nickel-only vapor around its hull. The second theory is less comfortable. Conditional contact. Here, 3i Atlas is not just pre-programmed. It responds. It might have cruised quietly through interstellar space for ages, only waking into active navigation, when it detected a certain threshold of technology or radio noise from a system. In that case, the timing matters. The shift toward Earth's orbit would be a response to our electromagnetic footprint. In other words, we pinged the sky for a century, and something finally pinged back by changing course. If that is true, it implies a kind of logic. Some decision-making process inside or behind the object weighed new information, then chose to intersect the path of the loudest planet in range. Whether that leads to contact, remote study, or something else entirely remains unknown. It would also mean that our presence is not a surprise. We have been broadcasting our existence across light years. This might simply be the universe returning the call. The third theory is the quietest and darkest: calibration. In this view, 3i Atlas is not interested in us as individuals at all. It is testing our systems. By executing an overt but deniable approach, it can measure how quickly we detect anomalies, how we handle missing data, how our political and scientific institutions respond under pressure. It does not need to land or send a message to succeed. It only needs to watch us scramble. Seen through that lens, the blackouts, canceled briefings, and internal clampdowns are not just bureaucratic frustration. They are part of the experiment. A way for whoever built the probe to gauge our maturity, our transparency, and our ability to coordinate across borders when faced with a shared unknown. If that is the test, our split between public silence and private alarm might not be the grade we want. There is a more mundane possibility that we have to keep on the table. That all of this, from the strange pulses to the nickel vapor to the converging orbit, will eventually resolve into a new chapter of natural physics. An exotic comet that teaches us something we never knew about how ice, rock, and metal behave under extreme conditions and long cosmic journeys. That is still possible. The universe is inventive. It does not owe us simple stories. For now, though, we live in the narrowing corridor between what the data shows and what we are willing to say out loud. An object from the dark between stars is changing its path in ways that look calculated. It is aligning with the orbit of a world that just began to shout its presence into space. Our instruments are watching. Our institutions are hesitating. And somewhere out there, 3i Atlas continues to glide on its invisible rails, breathing in the dark, keeping time, and closing the distance.